Hello. This video summarizes the main points of the paper that looks at using control theory and MAPE together with machine learning to create better adaptive systems. The approach is to use the strengths of each technique and create a layered system where they complement each other. The paper also proposes some open research questions that can inform future work. The name of the paper is Towards Better Adaptive Systems by Combining MAPE, Control Theory, and Machine Learning. It has 10 authors, which are Danny, Bradley, Masako, Alberto, Marin, Necmiye, Colin, and Kenji, and they're from various universities around the world. It was presented at the 16th International Symposium on Software Engineering for Adaptive and Self-Managing Systems, also known as SEAMS, which was held from 18 to 21 May in 2021 virtually, but it was originally going to be in Madrid. There are two established approaches to building adaptive systems that both work well in different contexts. Control theory is good for keeping system variables at set points or within desired ranges. This can be used to control things like the number of threads or buffer sizes. Control theory does not usually map well to complex software systems. MAPE is an architectural approach that identifies the functions to be performed as monitoring, analysis, planning, and execution over a knowledge base. MAPE has a global view of the system and addresses adaptation of software rather than physical properties or resources, and it makes decisions to manage trade-offs between goals. Machine learning has become more popular in recent years and therefore has become more interesting for using in the building of adaptive systems. For instance, classifiers can be used to reduce large adaptation spaces for planning. For MAPE, models of the system can be learned. For control theory, adaptation rules can be learned. These three building blocks can be combined in many ways for many systems, but there needs to be more work done to try different combinations. This is still a problem because MAPE, control theory, and machine learning are areas of active research, and we need more work to investigate how to use all three together. As research goes on, there will be even more approaches within each area that can be combined. The paper looks at a selection of related work. Some approaches combine MAPE with control theory, and others combine MAPE or control theory with machine learning. For MAPE with control theory, a conceptual model with three interacting feedback loops was proposed. The loops monitor requirements, manage context information, and control the target system. In this case, MAPE was used for the first and second, and control theory for the third loop. The higher level loops control the set points for the lower level loops to ensure goals are met. Machine learning has been used with MAPE to monitor computing systems at runtime and provide useful information. It has also been used for decision making when the space of possible adaptation grows too large, or getting information from large data sets like network flows. Machine learning has been used in a control theory context for model and system identification. For example, to derive a linear model of a system or solve highly nonlinear control problems. When the number of controller parameters that need to be tuned is large, reinforcement learning has been used. This paper poses the research question: how can MAPE and control theory be combined with and supported by machine learning techniques to produce better adaptive systems? This paper contributes concepts and scope for the three areas. For control theory, the strengths is keeping variables at set points. MAPE addresses the adaptation of software and has a global perspective. Machine learning can help with high-dimensional or voluminous data. A characteristic of control theory is that it has both discrete and continuous time models, it preserves system properties, and it has atomic control actions. MAPE has a complex combination of sensor data and is able to keep a complex relationship between observable data and properties of interest, and can combine complex quality goals. It also has a long timescale and can switch modes, handle structural variability, and deal with known complex actuation. Machine learning can build models and reduce complexity when building them. It can also estimate properties and optimize policies and design control input with deep reinforcement learning. The insights contributed by the paper are the characteristics and strengths of both control theory and MAPE and how machine learning can support adaptation techniques. 2. How CT and MAPE can be combined with supported by machine learning. And 3. A number of open topics for further research in this area. This is better because it applies these insights to build a model of a cloud enterprise system. The authors envision this could be applied to a web or IoT application, and Modelica was used for the model. The approach was to combine the techniques into 4 layers: the goal layer, the MAPE layer, control theory layer, and machine learning layer, as seen in the diagram. The goal layer converts application goals to technical goals, for instance, an SLA to response times, so things that can actually be measured by the system. The MAPE layer monitors the goals and makes reconfiguration decisions and changes set points for the control theory layer. The control theory layer uses these set points to control local parameters like thread counts and buffer sizes. Machine learning is used to generate load over time and required data output models that are used by the MAPE layer. The MAPE layer optimizes in timescales of minutes, while the control theory operates in milliseconds to seconds, allowing for very fast response times. While the MAPE allows it to adhere to goals and be well informed with good models from the machine learning. The control theory layer also considers the number of computational units, and the MAPE layer tries to accommodate it. So as the control theory layer decides it needs more threads or more virtual machines, the MAPE layer can see if those are available and if they are within the right parameters like costs and things, which may have been set, because not all goals will always complement each other, because you can have a very fast performing system, but at what cost, especially on cloud providers where you can sort of scale a lot, but you can also blow your budget very quickly. So, for the evaluation, the results show that the adaptations applied by the MAPE/machine learning layer enable the underlying control theory layer to better manage temporary infeasibilities. MAPE and machine learning are good at dealing with the complex information and adapting the system, as can be seen in the compute unit allocation and the response times in the graphs, with the MAPE and machine learning layer being turned on and off. You can see that it in the graphs that it doesn't really, without MAPE, it won't really scale down as much as with the MAPE, changing its set points and that sort of thing. So some small critiques, they only implemented a model, so there's no implementation or code base that you could work off, but they do provide a very good overview of the concepts and the strengths and how to combine the different systems. Thank you for your attention.